We'll resume at 4 according to this clock. Okay?
That's true.
Huh?
That's true.
What is for we can get started, right?
Just 1 minute. That's true. Because then otherwise it will repeat as more than repeat.
Yeah, that's why I didn't want to, recall CVAR definition. Yeah, because people are memoryless. You have copy and forget CVAR definition again. If there's another copy again, it will be an infinite loop. As the number of copies go to infinity. Well, it depends on whether you're looking at losses or gains. I've forgotten which one this is. Yeah.
But that inequality will also say reverse based on loss and gain.
Well, actually, see, the point is, yeah, I've looked at this long back. I can't recall why this is like this. See, the point is, this is just a campaign point.
Right.
See, for me, somebody gave me this. I have to estimate this and optimize this. Don't care whether it's coherent or not, but to publish a paper, I need to say it's coherent. I don't recall, but offline we can look at it. I can clarify it offline. Yeah. Yeah, we can get started. Yeah. I think it is on. Okay, so yeah, some easy expressions for CVAR and VAR. This could be useful homework exercises. If X is exponentially distributed with some parameter mu, then its VAR and CVAR have these expressions. Okay, it can be written out. This is like F inverse or something. You use that. I mean, you want alpha probability at some point, so you can just invert the F and you will get this. Okay, you will get this because exponential CDF is 1 minus e power minus lambda, and then you invert. It's easy. And then CVAR, you can just use memoryless property to say that. I mean, later you'll see that, I mean, if I want to estimate VAR and CVAR of an exponentially distributed random variable, then what's the easy way to do it? Like if I give you n IID samples from the distribution of this X, do I have to come up with some difficult scheme to estimate these two, or is there an easy workaround? What do I need to estimate these two? Somebody said, yeah, I just need to know mu. So as long as I estimate mu, I'm fine. Okay. A similar story for Gaussian case also. So for Gaussian case, these VAR and CVAR. So this Z is a standard normal here. Okay. So this can be treated as a constant. So it's like mean plus variance times a constant. In fact, as an aside, if you take Gaussian, if you have a bandit problem with Gaussian arms, then if you're optimizing CVAR, effectively you're doing a mean variance trade-off. We're doing mean variance trade-off because it's mean plus okay, standard deviation times constant. Okay, so the point is, in special cases, in general, this does not hold. This mean variance trade-off will not come for any distribution. But for Gaussian, it so happens that the expression comes like this. So again, if I estimate sample mean, if I take sample mean, sample standard deviation, then I get an estimate for both. Okay.
So Can you illustrate how C or each or is not subject in this example? What do you mean
No,
by
C
that?
bar is subadditive, var is not. I
How
can
is
show you an
subjective
example.
in, say, this first example?
No, take so take x plus y. Yeah.
See, it's a general property, right? So these are var C var for very specific distributions. The
So what
point
do you
is that
mean by subjective?
No, you take var of sum of two random variables.
Same
And then-
family or any two?
any two dimensions.
You need to, and
Oh, I see. Okay.
I mean, then this
Okay.
will be violated. I can show you an example. Offline, I'll show you.
No,
Yeah. Okay, but C bar will guarantee this because it's yeah. Okay, so this is about C bar. There's a generalization of C bar. I mean, okay, I just want to show you one version of C bar. Just remember this. It's like expectation of x given x greater than var. Okay, so it's like I can integrate the density from alpha to 1. Like if you take this expectation for a continuous random variable, okay, what is the probability that x greater than b alpha? Can somebody tell me? Anyone? What is the probability that x greater than b alpha? No, just this probability. What is the probability that x greater than r? It's a quantile. 1 minus alpha. So I just have to take 1 by 1 minus alpha, integrate from alpha to 1 of the density. That will give me C bar. Okay, I just want you to remember that because I can generalize it and make up what is called a spectral risk measure. Spectral risk measure takes all values between 0 and 1. Okay, and then this F inverse is like the var at level beta. Okay, F inverse is like the var, and this is how much it hurts. Like you take each quantile on the x-axis, it's like a loss value. If I lose 10,000, how bad I feel. If I lose 10 lakhs, 10,000, so on. For each of them, there's something I feel about. So I call this the, I don't know what I call this. Yeah, risk spectrum. I call this the risk spectrum. This can be, the easiest example is exponential function. Take an exponential function, as the losses keep going up, my pain exponentially, yeah, whatever. And so this phi, as long as it's increasing and integrates to 1, this is a covariant risk measure. What is interesting is if I put this as 1 by 1 minus alpha for all values of beta greater than alpha and 0 elsewhere, then this just becomes 1 by 1 minus alpha of integral of this. Okay, and that is just, C bar. That's just C bar. If you just eyeball it for a while, you'll see. This is like, this is a generalization, and it's a nice generalization because what is C bar saying? C bar is saying, until that var point, I don't care about the losses. And all the losses beyond that quantile, I feel the same about it. You understand? Because this is just 1. Okay, 1 by 1 is alpha, but it's the same thing. It's the same thing that I feel. Whereas what you could do is you could generalize and use an increasing function. So as the losses keep on increasing, I mean, I get more and more hurt and burnt and all that. Yeah. So that is captured in a spectral risk measure. It's a generalization. But while you generalize, as long as you maintain this nice property, phi increases integrates to 1, you stay within the class of covariant risk measures. So covariancy is kept intact. We didn't lose it, but we got a nice enough thing. So the point is, you're not looking at only one portion of the tail, and you're not treating all the losses equally. You can treat higher losses differently using phi. That's all there is to a spectral risk measure. And we'll look at estimation and all that. So, any questions about this? No? The 4 properties, covariant risk measure. Yeah, those 4 properties. Yeah. So as long as this happens, it's still covariant. Yeah. And hence convex and all that. Yeah.
So one question, what is the intuition behind like increasing the weight as you have larger values of x?
The point is, this is like a loss. So go back here at this figure. So imagine these are all loss values. Okay, and this is like with 95%, the maximum loss is this. So what C bar is doing is looking at all of this, putting a unit weight or 1 by 1 minus alpha. But it intuitively for humans, it makes sense that if I incur loss this much, it feels bad to some level with some weight. But if I incur a much higher loss, I should feel even more bad. So that's really the intuition. So what? So F inverse of beta is something on the x-axis. It's a loss value. Okay, you fix the beta on the y-axis, invert the distribution, you get something on the x-axis. So for each loss value, I attach a weight, and then I average it.
So in the bandit problem, the arm was distributed. You have a distribution of the arm. Now
Correct.
you have a distribution of the loss.
No, but this arm is, imagine you have some stocks, each, some stocks, you have K stocks, each stock has a distribution. So you could think of that as F for a particular arm. Now, instead of taking the expected thing that you get from a stock, you could look at this. Like that stock can give you a mean return something, but maybe it causes higher losses with, with higher rate, which you will, which you don't like. So this encodes the risk attitude. You understand? So in the expected return could be the same. I mean, the same example is here. Expected return could be the same for two arms. But the point is CVAR for this is here, for the CVAR for the other one is here. I would prefer this. But CVAR is more general. It's not about, okay, this you can say it's this mean variance. I don't want the spread to be more and all that. But in general, we need not have the same mean. So CVAR captures that. But the point is CVAR is just a tail measure. When you look at spectral risk measure, it's not just the tail. Every point matters. To answer one of Chandramani's question, if you want to be risk taking, just invert the exponential. Like you get more and more happy as you see more losses or something like that. Yeah, like you can be risk seeking with this. The phi function is yours. Okay, you fix the phi function, risk seeking, risk neutral versus all of that. Yeah. Okay, risk averse also. So that phi gives you the thing, but if it is increasing and integrates one, you get costs.
So P constant P will give us get us back to.
Yeah, usual probability x greater than x integral, assuming everything is positive value.
Right.
Other is there'll be some, you have to take positive and negative parts. Yeah. But if you assume losses are all greater than 0, then that integral with phi equals 1 is just the mean. It's just the mean. Yeah. So you get that, you get both sides. Yeah. Now to prospect theory. So this is some fancy figure. One of my co-authors from previous era like drawing these things. I drew, but he wanted stuff like this. So what happens is world throws rewards at you. But let's look at it as losses, and then the human evaluates this. And then this theory captures human preferences. Yeah. Any questions on this? No. Okay, we come back to this speaker route, suffer delay. And now the point is delays are stochastic, but the important point is, humans need not minimize expected delay. It's like, when you're driving on the road, something in us says that, okay, I'll take a detour and maybe reach office faster. Maybe there's a jam I'll avoid. That kind of ideas are captured well by cumulative prospect theory. Again, I won't do the poll because participation level is, it's law of small numbers. I want a huge audience where everyone raises their hand for something. But imagine you have two routes, just to illustrate this point. As I say here, route 2 has a lower mean delay than route 1. But route 2 slightly lower, not like in hours or something, a few minutes. But route 2 has a small chance of a very high delay because there's a chance of a traffic jam, maybe 2%, 3%, whatever you like. To get the right answer, I can keep asking this question with different probability, so that you'll finally say I prefer the route that you prefer. But yeah, each person has a tolerance. At some point, he'll prefer the route which has a slightly higher delay and avoids traffic jams. So previously, I would say humans prefer route 1, but then I ran into presentations where I had some vociferous arguments. Then now I say I prefer. Ran into it because somebody, I won't prefer this. How can you write? I'm also a human. Okay, yeah. So this happened, not exaggerating. So in choosing between routes, humans need not minimize expected delay. That's the only message I want to give. Yeah. So the way to explain this in a celebrated theory by Tversky Kahneman, they had a 1979 paper. Read this whatever subtext. And they had a later refinement in 92. We both have an idea which can explain human preferences, which is like not saying that in our brain we do it, okay? But if I do this kind of a manipulation, then I'll be able to explain human preferences. They didn't do any like experiments with the human brain or something, but just a suggestion of a model which explains human preferences. Just like, the example that I gave before, or the polls, if you remember, I did 2 polls where I shoot up a small probability, and then with that I'll be able to explain. So the same thing. So this is a mumbo jumbo definition, but we'll try to deconstruct it. So if you have just a positive value random variable, forget losses, okay, and then if you just don't have any W, and if you just don't have any U, then what you get is the expected value. Okay, you get expected value. Now what Tversky-Kahneman says, I look at gains and losses differently. So I'll split this into, this is like the positive part and the negative part, and I look at gains and losses differently, separate that out. And there's a utility for gains and a utility for losses. And these are not mirror images. The happiness I receive from getting 10 lakhs is not a mirror image of the, what sadness, melancholy I get from losing 10 lakhs. So you have a U plus and U minus. All right. And the other thing is they distort probabilities. So I won't integrate the probabilities as is, I distort them using the weight function. These are 2 things. This is not. It's here actually. Oh, there's somebody else. That's some. Okay, great. Okay, so whoever joined, I hope they can catch up somehow. So this is the connection to expected value. Now the point is what utility functions to choose and what weight functions to choose. Tversky-Kahneman suggested. What happened? This slide presenter went off. Something is on. Okay. Okay. Yeah, fine. So I'm not talking. Now I'm talking. Yeah. Anyway, this is the utility function they suggested. All right. So if you see, this is, I would say, I think whatever is here is all I want to say. The most important thing is the weight function for learning. Or, if I want to estimate, if I go back here, if I get rid of this weight function, if this is like expectation of some utility of this. So if I get samples from distribution of x, say x1 to xn, if I want to estimate expectation of u of it, then I just apply u to it and take the sample average. So it does not cause any problem in learning. So it's like a fancy thing that I can say in my papers, but this does not change any of my schemes. What changes is this distortion. The important thing to understand is you're taking probabilities and changing it. The way intuitively what you're doing is you're taking small probabilities or low probabilities and shooting it up a little, taking large probabilities and shooting it down a little. Okay, so that is the weight function. So if you remember that pole, if I had taken that small quantity 0.001 and if I had short it up a little, then I'll be able to explain all the preferences, both for losses as well as gains cases. So that's prospect theory. And to answer this question, you give me your weight function again, so this is a measure which, you give me any weight function, if you can turn this around or just go up or just go down, depending on your risk preferences. But in our work, we just assume that this function is holder. I mean, the campaign is cumulative prospect theory, where this function that is suggested is neither convex nor concave, but it is continuous and it's holder. It's holder with this exponent 0.69. So that's the weight function that Tversky, Kahneman recommended by experiments with human subjects. These were university professors. Where did they get the human subjects? Any answers? Grad students, yes. So this, and what is, like, you cannot, so money is not involved. What is involved? What was the payoff? Marks. That's correct. Perfect. So they did, like whatever I did, those two polls, they did those polls with saying that you get this much marks with this probability, things like that. Okay, and then they fit this model. But surprisingly, it's a very popular model. Okay, but my point is for the algorithms that I do, okay, any holder functions. All right. So at this point, I hope I've been very comprehensive in coverage of risk. This is the cool cartoon I got on this. I think one can be risk averse to whatever level. Yeah. After this, I'll get into estimation. But any questions about risk measures itself?
Just again explore it. You think that the holder function that you are referring has a non-integer differentiability exponent, the same thing that
What is non-integer?
means I am talking about the Lipschitz exponent.
The alpha holder.
No, it's alpha. It's alpha is 0.69.
That means it is the same like it is used in mathematical literature from the Taylor's polynomials. The function which is having non-integer differentiability.
That is the holder parameter.
That's the holder point. Alpha is 0.69. That's all there is to it. It's not Lipschitz. If it was 1, it was Lipschitz. It's not Lipschitz. The important point I want to say is the weight function that.
Lipschitz exponent, that's the alpha.
How can the exponent be Lipschitz? The function is Lipschitz.
And the functions, the continuity property is described by non-integer differentiability exponent.
I think this new to me will take it off. Anyway, so I want to look at estimation. And since this is a tutorial I'm giving, so I'll do some, marketing for my own work where I try to unify. So the question is, you are given IID samples, just like, mean estimation, you're given n samples, IID from the distribution of a random variable, no banded set, just one random variable in IID samples. And instead of estimating the mean, I want to estimate a risk measure from those IID samples. And just like what Krishna was talking about, Hawking's inequality, I want to get concentration. Why do I need concentration bonds? Because I need it for bandit algorithms. Okay, that's the goal of this tutorial. But concentration bonds are also of independent interest. You can use it in other applications also. And the first thing, what I'll cover here is I'll use a notion called Wasserstein distance to present this concentration bounds. I'll use Wasserstein distance. I'll present a unified bound that will apply to a half a dozen risk measures. Okay. Yeah. And I still got only one paper from it. Yeah. It's because only one proof. Yeah. We'll talk about it. Yeah. So the idea is I'll just use one general technique, one unified bound that will cater to CVAR spectral risk measure. And even it can be specialized, to get back mean, sample mean also. But there are direct approaches also, which I'll time permitting look at. Otherwise, you can look at the survey and dig further. Okay, so here are something. So the point is, this is an n sample estimate of the risk measure that I like. The risk measure that I like is rho of x, and I want a tail bound like this. Okay, and here is some table with some papers where people assume bounded support and got some concentration bounds for 3 risk measures, which I am talking about in this paper. Then for sub-Gaussian, there are some papers. Okay. And before I do this, I need to very briefly touch upon this notion of Wasserstein distance. If you don't understand Wasserstein distance well enough also, it's still fine. As long as you understand the estimator of the risk and the concentration norm, it's fine. Because this is coming from a proof artifact. We use this notion to derive concentration norms. If you can understand this, it's well and good. Yeah. So Wasserstein distance is defined like this. It comes from optimal transport. And you can see it as like, fastest way of going from one probability, one probability mass distribution to another. And this is like this can how much mass has to be transferred and things like that. And so this is the distance and all that. Okay, yeah. But the point is, this is the classic definition of Wasserstein distance. But what is interesting is, there are two other equivalents for one Wasserstein, which is this. If you have two random variables with corresponding distributions f1 and f2, then this integral is also the one Wasserstein distance, and this integral of the inverse CDF is also the Wasserstein distance. And if I take supremum or one Lipschitz functions between x and y, the supremum, that also gives me Wasserstein distance. And this is a useful lemma, simply because what happens is, I will use this characterization to give some bound for spectral S measures. I'll use this for CPT and I'll use this for C bar, things like that. So I'll use different characterizations of Wasserstein distance to relate the distance between C bar, or to relate the distance between risk measure of two distributions to the Wasserstein distance. Once I relate that, if somebody has derived Wasserstein concentration bounds, I will use that to derive concentration bounds for the risk measure. That's like the one-line message, but that's the reason why we use Wasserstein. Okay, and for this, important thing is, with Wasserstein distance, I think the most important bound is here. If you have a sub-Gaussian random variable, if you recall, these are the conditions. If you have sub-Gaussianity, if you have this, if Fn is the empirical distribution, does everyone know what an empirical distribution is, or empirical CDF? I hope everyone knows. If not, let me know. No? Yeah. Yeah. So, yeah, no answer is a positive answer. Yeah, it's not TC. Yeah. Anyway, so the point is, empirical distribution is like a reasonable estimate of the entire distribution given in IID samples. And so what happens is, now you are trying to see, so this is a distribution, empirical distribution, and F is the original distribution, the true distribution, and you're trying to measure how far this Fn, which is a distribution, not like me, it's a distribution, to this. So two distributions, how far they are, the metric we are using is Wasserstein. And this, what is the probability that this is greater than epsilon? Okay, and this is like this. This is something I derived out of some other bound and all in a recent work. So this is the bound. There's no 1 minus alpha. This is a mistake. So there's no 1 minus alpha. This you can forget. There's no 1 minus alpha. Yeah, and just a copy paste issue. Forget this 1 minus alpha, and then this is the bound I get. Now I'll use this and relate the risk estimation error to this for a bunch of risk measures. Okay, so this is just, if you're interested in knowing how I derived the concentration now, this is something which is a very useful tool, simply because I can relate many different risk measures, difference between two empirical and true distribution of two risk measures. I can relate to this for many risk measures. Okay, I've done it for at least half a dozen in this paper, at least half a dozen risk measures in one paper. Yeah. Okay, so we'll look at CVAR estimation. So I want to estimate this. Any guesses on what would be a good estimate? In general, if I want to estimate expectation of X, what do? You replace it by a sample average. Now what will you do here if I want to estimate CR? Any answers? Yes, no? Replace this by the sample average. That's all. Replace this by the sample average. Now this is some distribution. Okay, this is some distribution. So this, when it gets minimized, I think I can write something better. So you have infinite over psi plus 1 by 1 minus alpha, expectation of psi plus. Okay. This is C alpha of a random variable X. Okay. Now, if you take, imagine the random variable is continuous, and you say V alpha of X is like inverse alpha. This is like the Y. Okay, this is the alpha quantile. Okay, this is the minimizer. Okay, so if I take any distribution and do this, okay, that minimizer is var, and the minimum value is C bar. Right. Now, if I replace this by sample average, what is the distribution I'm looking at? I'm looking at the empirical distribution. So my var estimate will be, instead of F inverse, what will it be? If I want to estimate var, Fn inverse. Understand? See, the point is for a distribution, this can be any distribution with a certain expectation. We're taking this expectation of some distribution, which is two distribution. If I throw in the empirical distribution, it is F. So var estimate will be Fn inverse of 1. Then if I substitute that and get the value, that. So the point is C alpha can be written as, I want you to remember this. This is, replace this minimizer by V alpha. Plus 1 by 1 minus alpha, expectation of X minus V alpha of X. That is C bar function. Understood? You can do, this is just convex optimization 101. Take this function, differentiate, equal to 0, find that minimizer, that will be var. Assume continuity, we can generalize also. Assume continuity, your life will be even more easy. And so that value, if I substitute here, I get rid of the infimum because that's the minimizer, and that value is the C bar. Okay. So once I get var estimate, how do I estimate C bar? I replace this V alpha by V hat. Okay. Is this passage clear? Is this idea clear? Okay. So that's the next slide. See? So it bears a striking resemblance. Replace this by the true var, replace this by the true var, I'll get the true C bar. Okay. And this can be written as, this can in principle be written as, you can go back here. You can write it as here and replace this expectation by a sample average. Whatever you get is the C bar estimate. Okay, you understand this? So that's the thing. Now the next thing is we want to estimate this. But the point is, you know, when you look at the empirical distribution, this for the empirical distribution, I want to find a point where alpha amount of probability is covered. If you look at the empirical distribution, the gems are of size 1 by n. So I have to keep adding 1 by n until I get alpha. So it's that point where this, you know, this is that point. So you order those points and take this order statistic. That is the var. Because of the empirical distribution, it's putting 1 by n mass. So if you understand empirical distribution, this is what. Okay. Is this estimation clear? You want, if you, I mean, don't want to rush through it, but there is like a sound intuitive logic to this. Yeah. Any questions? No? Surprising. Is it after coffee? You know, people after lunch, you know, you have so much to ask, and after coffee, doesn't, yeah, it doesn't tally. Yeah, either the coffee is bad or no, nothing. Anyway, for this I can derive this concentration mode. Here there's a 1 minus alpha for a reason. Okay, so this is the concentration bound. This is in the spirit of whatever Krishna was talking about when he talked about opening. So forget all the constant. This is like roughly exponential of minus n epsilon square. Okay, so in terms of n and epsilon, you can't do better. I don't think you will get a n square there or anything. Okay, opening, that's the best thing. And I can easily specialize this. You can improve the constant. But in terms of n and epsilon, I think the dependence is optimal. And it allows a bandit application. That is something Krishna will talk about later. Any questions? Yeah. Oh, that's the E 2.71. Yeah. Whatever. Yeah. Euler constant.
What?
Just 2.7, whatever. Yeah.
So it comes to the water state.
Okay, it's probably a proof artifact. It's a proof artifact, but it's
Water state have, right? Water state quantification.
no, that it had, because we derived this. If you go back here,
Oh, that's an either. Okay.
there's an E there. It comes from there, but I put the E here. It's not from this paper. It's not from Lay's paper. So Lay's paper is for Bernstein condition. Though for sub-Gaussian case, when we did some rework of the proof, we got this. Yeah, this proof is there. Yeah, we got E. E was good enough. Maybe you can optimize, but yeah. Okay, so the point is, if somebody is interested in the proof, what we do is this difference. This is CVR of one distribution, which is empirical. This is CVR of the true. This is like some function of the true distribution. This is some function of the empirical distribution. This difference we say is that some constant times Wasserstein distance between Fn and F. And Wasserstein distance between Fn and F. See, this is some function of Fn, which is the empirical distribution. This is some function of F. So what we do is this we say is less than equal to some 1 by 1 minus alpha 1 by 1 minus alpha times the Wasserstein distance between Fn and F. That's what we show. Okay. Once we show that, any concentration bound for this will automatically apply with some constant scale. That's what we do. Okay. And we saw this connection first. Then we thought maybe this happens for other risk measures also. So the next risk measure is spectral risk measure. I want to ask how to estimate this. I mean, okay, I already have the solution. If I replace this by F, the true F, I get the true spectral risk measure. So I just replace this, with the empirical distribution. Now this difference I want to bound. If I get rid of this phi, then there is a Wasserstein distance form. It says that one Wasserstein distance, W1 of Fn, F is integral 0 to 1. Fn inverse minus F inverse beta. Now do you see the connection? It's like I want to bound the distance between this and the thing with F. So if this is bounded, I get rid of this. I get Fn inverse minus F inverse. So it's easily, if you want to see that form written better, this. Yeah, so I get this. So easily spectral risk measures was the easiest proof actually in terms of estimation. I related, so I can relate. So this one of them will be the true distribution, other will be the empirical distribution. Then I want to take phi out, so I'll just say phi is bounded. You will get a bound. That's all. So if phi is bounded by k, I take this out of the equation, I bring it down to the difference, I get this. And for this, there's a concentration bound, so I get a concentration bound for this. I won't bore you with the concentration bound, but if you have understood the approach, you know what I'm talking about. Got it? It's still in the same paper. See, it's like, unfortunately, a paper is like if you have one proof, one paper. Yeah, I've realized that. Yeah. I didn't know how to split it, but yeah, so I just, whatever I wanted to say, I said, yeah. And so at this point, we decided we unify it. So what we said was, if a risk measure satisfies this condition, which is like a holder continuity condition in the space of distributions. If the distance between two different distributions, when I apply this risk functional, is like holder. This is like a holder exponent. Okay. And this is the Wasserstein distance. If this is satisfied, then whatever bound I get on this, I can translate it to a bound on this, right? I can get a concentration bound for this. And what is amazing is, for CVAR, all these three risk measures, I get Lipschitzness. If kappa equals 1, it is Lipschitz. Okay, so these are all Lipschitz in the space of distributions. These are Lipschitz, kappa equals 1. And the L is all of these. Okay, there's another risk measure which I didn't talk about in this tutorial, simply because I thought there'll be too many questions on this. I'll not have any time to answer the questions. People, yeah, it's not much questions here. I'm not entirely sure if people are getting or I think, yeah, there's no.
You are missing the question.
Huh?
You are missing the question.
No, I was mentally ready for questions, and now questions have vanished into thin air, and I can't reconcile to that. Yeah, that's the problem. It's like, you go to a movie, it's a romantic comedy thing, and suddenly it becomes a horror movie. And then, no, I came for. Yeah, but this is the opposite. I signed up for a horror movie, but it's becoming a silent thing. Anyway, this is off the record. Don't put it on YouTube. Anyway. It's okay. Yeah, I still got my job. Yeah. So the point about what I want to make is there are several risk measures outside this. These are all nicely behaved risk measures. Cumulative prospect theory is not here. Cumulative prospect theory is not here. It's just outside. You can look at this paper for a proof. It's on archive. It's under review. A shorter version is in Europe's. So we have shown that a measure like cumulative prospect theory, which involves distortions. For non-trivial distortion, if I take that weight function to be identity, I mean, there's nothing. But for a non-trivial distortion function, this does not satisfy holder for anything. Yeah, we have shown that. It's not holder. It's not even holder. Forget Lipschitz. It's not even holder. Yeah. No, all of this, see, the point is this. I'll tell you like this. I can relate this to the Wasserstein distance. Now you give me a Wasserstein distance bound assuming anything on the distribution. Same thing will go here. So if you give me a Wasserstein distance bound, assuming the distributions are sub-Gaussian, then I get a bound for sub-Gaussian case. If you assume this is sub-exponential, I get this. So the bound I presented for Wasserstein was sub-Gaussian case. But if you look at the paper, I've handled sub-exponential also. See, this is assuming sub-Gaussian. Assuming sub-Gaussian, I wrote a bound. But in the paper we have, so if you take sub-exponential, it won't decay like epsilon square. It is smaller, it depends on epsilon. It's like roughly minimum of epsilon comma epsilon square or a Bernstein type bound you get. Okay, so I have bounds for sub-exponential case in the paper. So my point is, whatever conditions you derive Wasserstein bound will apply for the risk. So you give me a bound here, I translate. That's how it is. Yeah. And the same thing for unification. So this, the mega proof, 3 corollaries gave me 3. Okay, again, only one paper. Anyway, so how do I estimate? So the way to estimate for the general case, see, for spectral risk measure, CVAR and even the other one, I showed you the explicit estimate. The way in general you want to do is take the Fn and apply rho to that. That's my estimate. So if you look at this example, right, this was the true CVAR. How did I estimate CVAR? I replace this by the empirical distribution. So I can say that this is CVAR of Fn. It's CVAR of Fn, if that function makes any sense. Similarly, for spectral risk measure also, that integral, I used Fn instead of it. So it's like spectral risk measure applied to this distribution Fn. So in general, you apply the risk measure that you like to it. Okay, and so this, for this, I can get a bound, which is, this is the unified bound. Okay. This does not cover cumulative perspective. But it, yeah. And after this, I'll just cover CPT and then hand over to Krishna. But any questions so far about the bounds? Did everyone get the idea that I can unify? That's really the message I want to convey. Clear?
How loose are these bounds?
The constants are bad, but in terms of dependence, I don't think you can do better in terms of epsilon and n. You won't get a better power on n or on epsilon. You will get epsilon square. But whether this is 250, you can do certainly do better with constants. They are not, the constants are not optimal. And don't tell to this to my paper reviews. You know, Wasserstein distance bounds are conservative. I'll tell you why. It's like saying that you want one distribution at all points to be close to another distribution at all points. Okay. Now, if you look at CVAR was like, you know, looking at only one part of the distribution, the tail. I don't care, you know, the part where, you know, it is, you know, you don't care about until alpha. I don't have to learn the distribution amazingly well. It's the tail I have to cover well. Whereas Wasserstein, when I do these bounds, it's saying that the empirical distribution, the full thing is close. You know, so the constants are bound to be conservative there. Simply because you are saying you want the entire distribution to be close in terms of some distance or metric. So the constants are bound to be conservative, but what is the advantage? Advantage is unification. I write one proof, I can handle a whole bunch of measures. But if you want really tight constants, then what you have to do is, this is an interesting question which I am not going to answer fully. But the point is, look at this estimate, or I can go to CVAR estimate. So look at this CVAR estimate. If I want to directly give a concentration bound for this, what should I show? I have to show that this guy is close to V alpha. And then this is like a sample average. I want to show that this sample average is close. There's one tricky part is this is not the true thing. So if I replace this by the true V alpha, then it is just, you know, sum of IID random variables average converging to the mean. The tricky part when we do direct concentration is because this is there. Okay, so that's actually part of a paper which I co-authored with Krishna and someone else, where we directly derive concentration bounds for this. And I believe or I hope that the constants are way better. Yeah. Okay. So there, what we did was we took C bar, we showed that we had is close to that, and then we took this sample average and took the distance of the sample average to this, this expectation. If you look at this, if you look at this expectation of bar, so this we're showing that sample average is close to this expectation. That's like expectation of something with the sample average. The only tricky part you have to recognize is this is not the true bar. So not taking a sample average of expectation of x minus bar. So you have to do some work. That amount of work we did, we got one paper. Just for this. So direct approach. So if you're trying to, from academic career point of view, unification is not the best way. I think you take each risk measure and give a bound. Yeah, get more papers. That's
You had that expression for
huh.
can that as a risk measure also?
Yes, it is a risk measure. That's what I'm going to talk about. Yeah. No, it doesn't. No, the point is it's not holder. The condition that I wanted was in the unification, if I take CPT of one distribution and CPT of another distribution, I can't manufacture a holder constant and exponent. No, if it is bounded, yes, otherwise no. If the distributions are bounded, I can. Otherwise no. So my counter example was an unbounded distribution. So in that paper, I have an example which shows that for no such constant, yeah, there is a counter example, but it's not bounded. If it's a bounded, if it has a bounded support, I can easily do this. Because you have that integral, I can replace that by integral by m, and then that w, if you assume that weight function, I'll get to CPT next. So if I assume this weight function is holder and this integral limit is finite, I can get holder because this is like w of true distribution complementary and w of the empirical distribution. I'll apply the holder condition, replace this by the bound. Okay, otherwise I have infinity and I have to look at the tails. There's some tail part that will be left. That won't let you get to a holder condition. That's the problem. For unbounded case, you won't get it. So this is CPT. I think I'm just like 2 minutes away from finish. And let's see how to estimate this. So this is like 1 minus f of x. Okay, this is like 1 minus f of x. And this is like 1 minus f some other. It's like 1 minus f plus x, 1 minus f minus x. Now, what would be a good estimate? How do I estimate? Given n IID samples and an empirical distribution, if I want to estimate CPT, what should I do? By now, you should know the scheme. 1 minus fn plus, that's all there is. That's what CPT. So if you replace this by the true things, I get back CPT. But then the immediate question is, how will I do this integration? Okay, and you can look at this. If Fn is like this, okay, empirical distribution. 1 minus is like coming down a staircase, and you have to just look at a certain area, and that turns out to be this. Okay, now this can be easily done. Okay, you take those samples, you take the order statistics. Now I just want to show you the connection to sample mean. If I replace this by identity, what is this difference? Simple answer, huh? Yeah, it's a sample average. So now you understand. So if I replace this by identity, I will get 1 by n. So I'm taking each sample and weighting it by 1 by n. Then I get sample mean. CPT will be the whatever, like a mean. Now, what CPT is doing is based on where this guy is, based on where the W, this number is, whether it's close to 0 or close to 1, like that. So this difference, it is weighting differently. Okay. And that gives me this part. Okay. So it's not like, I made up a crazy estimate which has no connection to sample mean or something. This easily comes down to sample mean. The important problem is that if it is holder, learning becomes difficult. So if you remember this question, I won't get 1 by epsilon square folklore result for the holder case. W, this holder, if you remember that inverted S, shoot up low probability, shoot down high probabilities. For that, I will get a sample complexity like this. This is the bound. Point is epsilon power 2 by alpha. Or even bounded distributions. Epsilon power 2 by alpha, where alpha is strictly less than 1. Alpha is like 0.69 for the Tversky canon and suggested rate function. So this just means that roughly, if alpha equals 1, the number of samples I would need for epsilon closeness roughly is like order, sample complexity is order 1 by epsilon square, but otherwise it's more. So for CPT with the holder weight function, to get an epsilon accurate estimator, you need more samples. For the same estimate that I had here, this is the estimator. The point is this integral, one need not suffer, it's just a summation with some weights. After this, you do the same thing for the other one also. I didn't want to bore people, bombard the slide. And this is that. But we are assuming bounded support. For bounded support, I get this. And this has nothing to do with unification. This is a direct approach. Yeah. But from in that unification paper, I had another type measure, which is not holder continuous. And that gave me this bound. I don't even have the heart or time to describe this, but we used truncation. So if you take subgaussian, so the takeaway challenge is go look at CPT risk measure for a subgaussian case, try to manufacture a very nice concentration bound, which is better than this. Yeah. Yeah. We use truncation and all kinds. Yeah, but this also came from another class of risk measures, which is not holder. In the same paper that is there. And that's where I'll end. Okay, so for this, at least for the bounded case, I used this characterization. Okay. And I'll stop here. We'll not have coffee tea, but we'll have bandits. Okay. Any questions on concentration? So the direct approach is here. I mean, you can directly do this, var concentration and use this var concentration to derive a CVAR concentration result, stuff like that. I'm going to skip this in the interest of time because we have to talk about risk aware bandit. So I'll hand it over to Krishna. Keep it on. So.
Is everyone awake? Okay. Huh?
I am.
So, just wondering if how much absorption capacity is there at 5 o'clock? Can I just do Thomson sampling? Oh, okay. Okay, so let me just quickly gloss over the what's coming. I'll spend a little more time on Thomson sampling. So just before I hand it off, we covered regret minimization with UCB or LCB type algorithms, and then best term identification, right? That's all for me, right? So the big picture is that if you're using LCB or UCB, you had a Hofding inequality or sub-Gaussian concentration, and then applied a confidence form. Now, let's say you are minimizing CVAR or some risk measure, right? CVAR or spectral or whatever. You have a concentration that you have derived either through the Wasserstein approach or through a direct approach, right? So you have a concentration. You keep that as your building block. Flip that around. Remember that flipping argument? You flip that around into a confidence form, and you run an LCB algorithm or UCB algorithm. Right? So that's one kind of an approach. Then I'll also speak about some very interesting recent work on Thomson sampling. Thomson sampling, I haven't even talked about the mean case, right? So let's see if I get, I think I'll be able to do that once in half an hour. Okay. Okay, so now you have, going back to the world picture, you have some distributions, K arms, K distributions, some horizon N. now instead of earlier my slide used to say mu1 through mu k. Remember, there were the means. Now I have some risk functionals, rho1 through rho k. Maybe C bar or mean variance or CPT or something. Okay, it has some risk functional. Problem is the same. I have to pull an arm. I get a sample from the distribution, but now I'm not interested in the mean, but I'm interested in the risk function. All right, as given by the sample. So I want to, let's say this is best. For best arm identification, I want to minimize. I want to find the arm which has the lowest risk rho star, right, among all these arms. Or they can also define a risk regret, which is so a rho star is the best regret. If you play that arm for all the time, you would get n rho star. But your algorithm doesn't know the best arm. So if you will incur a risk rho I every time you play arm I, and you can similarly define a risk regret, just like I defined an expected regret, you can talk about a risk regret, right? So again, you can talk about two different problems: risk-aware regret minimization or risk-aware best arm identification, right? So I want to minimize expected regret or minimize the probability that my arm recommendation is not the optimal arm or something like that. Okay. So here the approach is the same. Okay. Except I'm going to use. See, this was a mu I. Remember? Now it's become a rho I. The LCB is built now using empirical construction of the risk. This could, for example, be CVAR obtained from your samples, right? Empirical CVAR minus some confidence rate. Now remember, where does the confidence rate came from in the mean case? It came from a Hoffning inequality or a subclassic concentration inequality, right? So now this W's are going to come from a risk functional's concentration inequality, right? And they flip that around into a concentration. That's the idea. If you get that much at 5 p.m., I think that's all right. So Prashanth just showed some CVAR concentration, CPT concentration, some big expressions. Flip that around into a confidence bound, manufacture a confidence bit. You run a LCB algorithm. You can then get logarithmic risk regret. Okay. All right. I don't even know what this is saying. This is for Holder risk measures. So if you have a risk measure which is Holder in the Wasserstein distance, you have Wasserstein concentration which translates to a risk concentration. You manufacture WT based on that. Then you will get log if your kappa is 1. If you have Lipschitzness of if your risk measure is Lipschitz in Wasserstein distance, you will get logarithmic regret. Otherwise, you will get some kappa in the log t power kappa. But the idea is the same. Okay, there is no new concept here, right? The key is concentrations. Is your item, the risk measure of interest well concentrated, right? Like CVAR or CPT or whatever well concentrated. If so, you can manufacture a confidence bit, plug it into a LCB algorithm, get logarithmic regret. You can get logarithmic regret for Lipschitz case and log t power kappa for Holder case. All right, is that conceptually clear at least? So similarly, so this is basically, I remember I showed you gap dependent regret and the gap independent regret. You have what is this?
For kappa equals 1, the bonds of
Kappa equal to 1 is Lipschitz.
So all CVAR spectral is covered. The bond looks very similar to what we have for mean case. Same log n by gap.
So this is root of log n plus something whole square. So this is the logarithmic regret, right? And then you will get something. You will not get logarithmic regret in the worst case. So you will get some root n log n k type. Okay, so CPT likewise you have to truncate an estimate. Okay, and you can get so confidence with this has some alpha here, right? So that's the regret bound for CP.
That's weaker because to the alpha minus
That is it's worse, right? So you will normally get delta square. You get now it's something worse than delta square.
You put alpha equals 1, you get that. Now you're getting something.
Yeah. So that is so at a high level. if you have a risk measure which is well concentrated, you can flip it around into a confidence bound. Put a confidence, you can estimate the risk measure using your samples minus WI, which is manufactured using your concentration equality, and run an LCB algorithm. Okay, and analysis will be similar, maybe slightly messier, but it's similar. Okay, so key concentration, yes. Yeah. So this is for a fixed. If I fix the arm distribution, you run the algorithm. This is the regret you can get. Okay, upper bound. Now it's like adversarial. I fix the LCB algorithm. You come up with whatever distribution you want. Adversarial. Okay, and you know my algorithm. You can come up with whatever worst case you want. Those cases you will not get independent of, you will not get log n, or you will get some n power something, root n usually. Right, sorry. Root n for CVAR and all that. For CPT, you will get worse than root n. Right, you get n power 2 minus alpha. It's not. It is sublinear. So this alpha, it's 2 n to the 2 minus alpha by 2, right? Which is n to the 1 minus alpha by 2. Alpha is between 0 and 1. Alpha equal to 1 is Lipschitz, like CVAR and all that.
If you put alpha equals 1, you get square root n. You get something more.
Okay, so now I have half an hour. So maybe I'll spend 20 minutes or 15 minutes or something like that on Thompson sampling. Okay. Okay, so Thompson sampling is a Bayesian update strategy. Okay, a Bayesian algorithm for bandit learning. Okay. This so the idea is that you keep a prior and you keep getting samples, and based on the samples you get update a posterior and keep proceeding like this. Okay, it's a typical. I'll show you the algorithm in full detail. Around 2012 time frame, it was shown. There were 2 papers I think which came up independently. There was Agarwal and Goyal 2012, which showed that Thompson sampling is optimal for Bernoulli rewards. Okay, optimal in the sense not only does it get logarithmic regret, the constant in front of the logarithm is also matches the min-max lower bound. Okay, which comes from an information theoretic argument. I think Emily Kaufman's thesis also around that time, 2012, she had a paper on, Emily Kaufman had a paper showing the optimality of Thompson sampling. This is all 10 years ago, all right? The issue with Thompson sampling, see, Thompson sampling is known to work well, but since it's a Bayesian update algorithm, it is easily analyzable only for certain classes of distributions. So for Bernoulli, it's well analyzed. Bernoulli binomial and all, it's well analyzed. Gaussians, it's well analyzed. Do you have any idea why? It's a Bayesian algorithm. Hint. Okay, Bayesian algorithm. Gaussian arms. Huh? Yeah. Conjugate. Yes, conjugate. You see, Gaussian is it's posterior stable, right? The posterior distributions are also Gaussian. So Gaussian arms, you can prove something about Bayesian sampling being optimal. Likewise, for Bernoulli or binomial rewards, they are not posterior stable, but the conjugate distribution is well characterized. It's beta distribution, right? No, this is a very, maybe I'll show you the Wikipedia article on this. I had pulled it up somewhere. So on conjugate prior. So what I mean by conjugate prior is, you just look at this, right? Let's say you have a Bernoulli binomial distribution, okay, like so. You see this, right? This is a binomial distribution, and Q is my success probability. All right. If now Q itself has a prior which is beta distributed, like that. Okay. If that is the case, you can show that the posterior. Now, if you get posterior samples of successes and failures from this binomial, the posterior update of the Q, right, will be also, if you just, this is just a undergraduate level Bayes rule calculation, all right? We just work this out. It comes out to be another beta distribution, okay, whose parameters are updated as You just add to the alpha parameter of the beta distribution, you add the number of successes, and the beta parameter, you add the number of failures. Okay. So the point is that if so, when Shipra Agarwal and Goel analyzed this for Bernoulli arms, they were using this conjugacy prior conjugacy to analyze the algorithm. But I haven't told you what Thompson sampling is. I'll get to that. Okay, it's just a prior posterior update algorithm. Okay, but the point I'm making is that in all of the analytical results available, people used to assume either Gaussian, which is posterior stable, or binomial, whose conjugate distribution is the beta. Some people pushed it to multinomial, whose conjugate distribution is Dirichlet, and all that. So there is, if you go down this article, you have a whole bunch of the whole table of priors and posterior conjugate priors. Okay, binomial, Bernoulli, beta, Poisson. So if you want to write a Thompson sampling paper with Poisson arms, you update a gamma distribution, you can write a paper technically. But the issue was that it was only proven to work well for these very specific categories. So multinomial Dirichlet, normal, inverse gamma. So there's a bunch of distribution for which it was known and people could write papers on this, right, for these category of arms. But then in bandit, so in learning, we don't know which category it's going to come from, right? You have to assume some sort of a general distribution. So the issue with Thompson sampling, although it was known to work well and optimality was established for certain Gaussians or binomials and all that, it remained a little bit of unsatisfactory thing that you could not say something about its optimality in general, right? Or even some class of distributions, which is not, one of these nice families like like normal or whatever, right? So this was overcome in what I think, and Prashanth agrees, is I think a very deep paper in 2020. Okay, Rue and Honda. Okay, a very impactful paper showing the asymptotic optimality of Thompson sampling for mean. Forget risk for now. Okay, just for mean estimation, mean bandits. They showed asymptotic optimality of Thompson sampling for first multinomial, whose conjugate is Dirichlet, and then they pushed it to any bounded distributions. Okay. Yeah, so I think so for any bounded distribution whose rewards are bounded, Thompson sampling is optimal. Okay, you cannot beat it. The sense that the term in front of the logarithm, in terms of degree, term in front of the logarithm is also optimal. Okay, and this was shown in this paper. It came out during the pandemic, and my sense is that it has gone under the radar. I think it's not. No, I would put my stick my head out and say this is probably the most impactful paper after Oyer's analysis in 2002 in bandits. Okay, this I think is a deep paper, and it's one of those papers which I think you're left wondering how the authors came up with it. Okay, so I'll just tell you the algorithm. Okay, I haven't fully digested the intricacies of the proof and all that myself, but I think this Rue and Honda is a very important paper. Okay, this is only for mean bandits. Then Emily Kaufman and her collaborators, students, etc. Last year's ICML, they pushed it, the same technique of Rue and Honda to CVAR regret for any bounded distribution. So this is for mean regret. Similar techniques pushed for CVAR regret. Okay. So these are papers we will briefly discuss. There's also Vincent Tan, our co-author in that survey paper, also had a ICML 2020. He had a very nice paper on Thompson sampling for mean variance bandits. So you have now your risk measure is some combination of mean and variance, linear combination of mean and variance. Okay, where Gaussian is a little more tractable. This was pre-Rue and Honda. This was done for Gaussians. Okay. All right. So, okay. So first, let me tell you the more easily digestible or believable algorithm in Rue and Honda, which is multinomial Thompson sampling. Okay. Multinomial is a generalization of binomial, right? Binomial, you have successes and failures. Multinomial, you have categories, m categories, right? And each has some. How many of each category did you get? Is the that you probably know the PMF of multinomial. Anyway, so you have bunch of multinomial arms distributed without loss of generality over some n plus 1 points. Okay, so you can take this as anything, but they have just taken it as 1 by m, 2 by m, etc. You're given a horizon, you're given number of arms, multinomial support size m. Okay, so this the way it works is that you sample from a conjugate distribution. Okay, so you initialize with, let's say, all the multinomial parameters as 1, and then you sample from the conjugate distribution of multinomial, which is Dirichlet. So if you're in the original paper of Agarwal Goel, the arms were binomial or Bernoulli, and you would sample from a beta distribution. Okay, and you will sample, and then once you have the sample, you go and find out. So this LK is a Dirichlet sample, which has m plus 1 dimensions, and then you calculate which. So you do this for every arm k, all right, and then you find the arm which has this maximum average reward, so to speak, right? So these are the so this is the sort of the the empirical reward is highest, and then you play that arm. Okay, you will get some reward of the form little m over m. Why? Because the arms are all multinomial, so it will be of the form m by m. And then you update the parameter, the alpha parameter of the multinomial goes up by 1 for that m and that I of t. Okay, and then you go back. Again, you sample from a Dirichlet with the new alpha parameters. Then you again generate, you play the arm, and you keep going like this. Okay. So, yeah, so this is a posterior update. Okay, so you have an arm index coming from the sample you get, determined by the sample you get. You play the arm with the maximum I of t, and then only for the I of t arm and the reward you get, you update the multinomial parameter, and then you go back. Okay. So for this, it was shown that for multinomial rewards, they showed that these alpha parameters corresponding to the Dirichlet distribution converge to the true multinomial arms for each arm, and then therefore the algorithm will very quickly learn the best multinomial arm. Okay. I think so. There was, and see, I would say this is a generalization of the beta analysis of Goel and Agarwal, or even Emily Kaufman's analysis.
I think it was on paper that discusses concepts for MVPs.
Of?
MVPs.
Okay.
So I think there also there is sampling from distribution.
See, that will you have to, right? Because if you're having multinomial, they are duals, they are conjugate priors. The issue is that this paper then showed optimality. See, it is not surprising. Any Thompson sampling paper working with multinomial arms has to sample from Dirichlet. That is not surprising. That is the way it has to be, right? But this paper then showed optimality of Thompson sampling for multinomial arms. Then they pushed it to bounded distribution. Okay, this was not for 50 years. Wait, hang on.
There is a query here. So the question is this different from usual Thompson sampling, and then samples of reward are not taken, but the posterior mean is compared to every session?
I'm not sure. I think this is, see, I don't think this is conceptually any different from what you would normally do. I think this is just you can say it's a generalization of the analysis for beta distributed rewards, Bernoulli distributed rewards, for which the conjugate prior is beta. Then, okay, so this is the algorithm which I find mysterious. This is called non-parametric Thompson sampling. Okay, and this was shown to be optimal for any bounded distribution. Okay, they've taken bounded in 0, 1, but it would also be bounded in 0, b. Doesn't matter. Okay, so you again, what you do is you sample. Okay, I've said Dirichlet distribution. So nk is the number of times you've seen arm k, and xk is the rewards of arm k. Okay, you initialize xk as 1, nk as 1 for each k. then you go ahead. So nk is the number of times you played arm k, right? You go ahead and generate, you sample from a, I've said Dirichlet distribution of 1, 1, 1 of nk, which is actually sampling uniformly from a simplex of dimension nk. Okay, so this is uniform sampling from a simplex. Okay, so if you have an n-dimensional simplex, you sample, well, that's a continuous space, right? 3-dimensional simple, 2-dimensional simplex is like a triangle and whatnot. So you have a uniform distribution on that and sample uniformly from that. You end up with the probability vector, correct? Now you take, so this pk is a probability vector. I have written Dirichlet just to maintain continuity with the multinomial case, but it's really a uniform sampling from a simplex. Okay, and then you take, so this pk is a distribution, and you use that pk, which is actually just a probability vector if you think about it, of size nk, and you take all the rewards you've gotten so far on arm k, and you weight it by this probability vectors. Take inner product. Okay, so you're sort of randomly reweighting the rewards that you've seen so far. Okay, the clear. So xk is a vector. Okay, it consists of all the rewards I've seen from arm k. All right, and I have this pk, which is also of the same size. It's a probability vector of the same size. How is it obtained? Sampled uniformly from a simplex of that size, and then you take the inner product of these two. All right, and then for whichever k maximizes that inner product, you play that out. Okay, and of course you will get a reward. And what you do with the reward, you just append it. Okay, there is no, so this is not a parametric Bayesian parameter update algorithm. Okay, it's a randomized algorithm. It looks somewhat like, it's not really even Thompson sampling. Okay, it's inspired by Thompson sampling. Okay, and of course NT you have to do NIT is equal to NIT plus 1 because you have got one more award, and XIT alone you append. Now you have a longer vector for that arm. You go ahead and do the same thing. You keep doing this. Okay, and so is the algorithm clear? Algorithm is easy to understand. So if you can think of it, so it's the support of the distribution. So you have a bunch of awards on arm k, right? And you're taking some random reweighting of this award, of these rewards. And that random reweighting, the coefficients are drawn uniformly from a simplex. Okay. And they showed, I think this is the influential result. I mean, for this algorithm, they proved that the regret is delta I log n by k infimum, which is the smallest KL divergence among all distributions with whose expected award is greater than the mu star or mu1 or whatever the best reward. Okay, so KL divergence is the, yes. This is the algorithm. I mean, if there are any questions in the algorithm, you let me know. Yeah, so Dirichlet with sample 111 is just uniform. That I hope is clear, right? But the point is that it's of dimension nk. So it's like you're sampling uniformly in a simplex of dimension nk. For each arm, yeah. Yeah. So arm 1 may have 21 samples. You will generate a 21 long probability vector by sampling from a 21 dimensional simplex, and you will take inner product with the vector of rewards you've gotten so far. Yeah, so the xk keeps increasing in size, correct? And so you have to sample from a larger and larger simplex as you keep going, right? The result is that, so you have not only logarithmic regret, but the constant in front exactly matches the lower bound for regret from a 1996 paper. Okay, so this is for any bounded distribution. Okay, so in some sense, I feel this is like the final word. There is no, I mean, you cannot improve this. For any bounded distribution, this is the best algorithm. Okay, so I feel that it closes a chapter on bandits in some sense, right? So the lower bound is also this Burnett's as lower bound says greater than or equal to exactly the same thing, except the little o could be different. The little o log n could be different will be different, obviously. But the constant in front is exactly the same. Right? So it's optimal to that extent. Only additive factors could be different. Okay, so that is how good this mean reward, this non-parametric Thompson sampling is for mean rewards. So it exactly matches the lower bound for regret. So the Thompson sampling regret proofs typically follow pre-convergence and post-convergence analysis of the conjugate prior. So what I mean is that, so if you're working with binomial rewards, you will have a beta distribution, and you will basically show that the beta distribution that you keep updating is converging to the true beta parameter of the underlying arm, which is the probability of success. And likewise, the Dirichlet parameters are converging to the true multinomial parameters, something like that. And there are two-phase analysis. So all Thompson sampling algorithms are analyzed in two phases: pre-convergence regret, post-convergence regret. Pre-convergence means the parameters haven't converged. Post-convergence, after convergence, how much exploration does the algorithm do? And that's what they do. They show that the pre-convergence regret is order 1, post-conversion regret is this much. Okay, so it converges for multinomial Thompson sampling. The convergence takes place in order 1 time. Okay, that's for multinomial Thompson sampling. The non-parametric Thompson sampling, which I think is the most remarkable algorithm, there's no parameter if you think about it, right? You just keep on appending the reward vector. You sample from a simplex, take inner product, you play the arm with the best inner product, and so on. Now the question is, what is converging here, right? In the Thompson sampling, you say parameters are converged, so I am identifying good arm. So it turns out that I think this is the deep part of the paper, that they actually look at the empirical distribution of rewards from each of the arms. Okay, so each arm has a reward distribution, right? And then you're getting some rewards, the samples, right? So there's an empirical distribution. And then what they look at is a Levy distance between the empirical distribution of each arm and the true distribution of each arm. Okay, Levy. So we've seen one Wasserstein distance between two distributions. Levy metric is another metric between two distributions. Intuitively, if you have two distributions F and G, let's say you have two CDFs, the Levy metric is you try drawing squares between these CDFs. Okay, you have one F1 and another F2. You draw squares between these CDFs. Okay, so that it's contained between the two graphs. What is the side of the largest square you can draw? Okay, that is some whatever, right? If the distributions are very close, you can draw a very small square. It turns out the side of the square, which you can inscribe between the two graphs, actually constitutes a metric in the space of distributions. That's called the Levy metric. Anyway, that's an aside. It has nothing to do with bandits. It's just a metric, just like Wasserstein is the metric in space of distributions. This Levy is also a metric. Now, my point is that they look at the convergence of the Levy distance between the empirical distribution and the true distribution. And then they have pre-convergence, post-convergence analysis in this Levy metric. Okay, of the reward, empirical reward to the true rewards. Okay, so that is how their analysis proceeds. And I mean, you can understand the equations, but I'm still wondering how they worked it out. It's one of those mysterious papers, and I think it's one of the, it's a 20-year. I think it's one of those papers that comes every 20 years or something like that. You know, I think it's a great paper. Anyway, so this is for mean regret. Okay. So Ru and Honda. So if I said earlier, Audibert and all that, right? 2010. So this is another paper you can read. You really have to read 3 papers from this tutorial, maybe. Then Baudry et al. This is that Emily Kaufman and co came up with an algorithm for CVAR regret. Okay, using Thompson sampling. Yes. Yes.
Yeah. So, do you have any intention why they are sampling uniformly? Because you not want to uniformly sample, because as your vector size is decreasing, you may want to weigh them differently.
Yeah, you weigh them differently. That's the point. See, in the step, the way you weigh the weight assigned to a particular reward is different. but those coefficients are chosen uniformly from. See, I'm not saying that these pKs are 1 by nk. That's not what I'm saying. It's uniformly drawn from a simplex.
Should not be uniform interchange.
No, they are weighted differently. I agree with you that they're weighted differently already. But the weights are determined in a uniformly random manner. So it's some kind of a random distortion of the underlying distribution that's going on. So you're getting some empirical distribution of the rewards, and they are contorting it in some randomized way. Okay, and they are looking at, so this is an expected value of that distortion, okay, in some sense. And in the paper of Baudry et al., they do the exact same thing. You have a sample. Now I have written sample uniformly over a simplex. This is exactly the same as, maybe, I don't know, should have written the same thing previously also. The step is exactly the same. This is CVAR. Okay, this is for CVAR. Now earlier you did inner product PK transpose XK, right? PK is just some distribution of size XK. Now you do a CVAR. C alpha of XK comma PK. So you're just looking at the CVAR, empirical CVAR of over a support of XK, but probabilities are like PK. And then you play the arm which has the best IT, and then you update your NT like this, and XT you just append the reward. Okay? And then you proceed. Okay. So the only difference in this step is that instead of taking a weighted average with PK as coefficients of your past rewards, you're looking at the CVAR, which is the objective of the metric of interest here. Otherwise, it's exactly the same. So the algorithm is, it sort of comes directly. Instead of average, you replace with CVAR, and so this is non-parametric Thompson sampling for CVAR. Satisfies exactly the same kind of bound, except this delta I alpha are CVAR alpha gaps, and K alpha in for is infimum over all the KL divergences of those arms which have greater CVAR than the top arm. Okay, actually I should be, okay, I think Baudry et al. Look at maximizing CVAR. In the stock we will be minimizing CVAR. It doesn't matter that much. Okay. So the authors in this paper, Baudry et al., they also show that this algorithm exactly obtains the lower bound. No, sorry, this algorithm obtains this bound, and no algorithm can do better because there's a lower bound from information theory considerations for CVAR regret as well. Okay. So finally, I want to. So any questions on this?
Yeah, so there is a query.
Yeah. Yeah, this is for any alpha. This is for any alpha. It's optimal for any alpha bounded distribution. So CVAR regret also Thompson sampling is optimal. What is this? Not non-parametric Thompson sampling is optimal. You cannot beat it.
No, it's asymptotically.
Yeah, you cannot. Yes, asymptotically optimal. This term is different. Finite n, we don't know, right? Very small n, you don't know which is optimal, but large enough n, you cannot beat. Okay.
So there is a criteria. How is CVAR of X and P, two arguments, defined? Earlier, the definition was for a random variable X with some distribution.
Good question. Okay. So what is this beast? You think of this, you think of the alphabet of the distribution as the empirical reward seen so far. Okay, so the kth arm has 21 rewards seen so far. That's a 21 big alphabet over whatever, right? Those rewards that you got. Now you are also looking at a probability vector coming from a 21 dimensional simplex. Okay, now you think of this as a probability distribution over the support of the reward that you've seen so far. That CVAR is well defined, right? So you think of XK as the alphabet over which the distribution is defined, and PK is the distribution, which is coming from a simplex. Okay, so a good question is a good question, but it's essentially the alphabet over which you are taking this mean or CVAR depends on the previous rewards. Okay, it's not a fixed alphabet. Multinomials has a fixed alphabet. This one is not fixed alphabet, depends on the previous rewards. Okay.
So you do not seem to be favoring less explored arms as in UCD or in earlier concepts. Earlier, you somehow thought that was reasonable. Here you are not doing that.
I think so. The exploration, as far as I know, okay, I don't. So if you just go to View Honda, they make a remark about this, which I don't recall off the top of my head. It has something to do with starting with one reward for everybody. Okay, and then so that ensures that every arm has a non-zero probability of being played. So this PK, you're sampling uniformly from a simplex, and with probability 1, you will be in the interior of the simplex. You're not going to put 0 weight on anybody, right? Because you're not going to be on the boundary, right? So that ensures that every arm has a non-zero probability of exploration, and that is enough. They show that's enough. Yeah, there is a remark in the paper. You can see that paper. Worth reading. I am running out of time. I had one more Thompson sampling algorithm of Vincent Tan's paper, but this is mean variance Thompson sampling, where the metric of interest is not CVAR but some combination of rho times mean plus variance. Here, what you do is you sample from, for the mean, you sample from a Gaussian, and for the precision, which is 1 over variance, you sample from a gamma, which is the prior conjugate of variance. Okay, and then the rest of the algorithm is along predicted lines. Okay, they get some regret. Okay, so this is somewhat, I mean, this is somewhat standard, I would say, although it is technically demanding, but it's believable. Maybe in 2 minutes I have, you know what? I think we're just out of time. It's 5:30, right? I had some more slides on best arm identification. So maybe I'll just tell you some papers in this. Prashanth, myself, and my student had CVAR concentration for a bunch of distribution classes and a CVAR successive rigid algorithm for the least CVAR arm. Okay, best CVAR arm identification. Jagannathan Nair, who spoke yesterday, his student Kadvecha et al. We had a paper in NeurIPS in a distributed oblivious setting, and the objective was to minimize a convex combination of mean and CVAR. Okay, I had a slide on this. Okay, so the point of remark in this paper. Okay, so this is the paper, this NeurIPS paper. So the objective of interest is some convex combination of mean and CVAR. Okay, the unique thing about this paper is that nothing is known about the arm distributions. So far everything we have discussed, we either know that the distribution is bounded support or sigma sub-Gaussian where sigma is known, or something of that kind. So this is a paper where absolutely nothing is known. Okay, we only assume that a 1 plus epsilon moment or some pth moment for p greater than 1 is bounded, but even the b and the p are not known. Okay, there exists a bound, but we don't know that. Okay, so absolutely know nothing. Okay, so in some sense, this is the most general setting, and this can incorporate heavy tails and all. You saw a tutorial from him on heavy tails. Right? He likes heavy tails. He's been doing heavy tails for 12 years now, right? So we did heavy tails with bandits, so here we are looking at. So we did heavy tails. We did CVAR and best arm identification. Okay, some linear combination of CVAR and mean. Okay, and xi equal to 1 means you are purely mean. You want to maximize the mean. Xi equal to 0 means you want to minimize CVAR or some combinations thereof. The key point, maybe I'll stop with this, is that the key challenge is that the empirical estimators perform very poorly. If you have heavy tail distributions, not sub-Gaussian or something, if you just take empirical estimators, sum over xi by n, you're going to get really poor concentrations because heavy tail distributions don't concentrate well. You know from yesterday, right? That the concentration properties are poor. So the key idea was to work with projected samples. So if your samples go outside a minus b to b range, you bring them back to minus b to b. The simplest step. Okay, so if your xi sample is outside this minus b to b, just bring it back. Okay, and you pretend that your sample is minus b or plus. If it's between, you pretend that it doesn't go with the actual sample. Okay, which is just this xi b. You can do, so our algorithm in this paper So you truncate or you project like so, and you can do successive rejects. Remember successive reject, which works over phases, or uniform exploration. You can equally divide your budget into K and do uniform exploration. Key being that this projecting, the minus B to B, if you keep it fixed, you're going to introduce too much bias. So this B also has to be scaled with your budget N. Okay, like N to the Q, where Q lies between 0 and 1. So N to the half or N to the 0.75 or something like that. With this projection, we could guarantee that both successive rejects and uniform exploration have e to the minus gamma N to the 1 minus Q probability of error. Probability of error, decays in the nice cases like sub-Gaussian, you have e to the minus constant N. Here, the totally distribution oblivious setting, we are not able to get e to the minus N, but we are able to get e to the minus constant N to the 1 minus Q. Okay. For N greater than some function of Q. Okay. The point is, why can't we push Q to 0? Right? If you push Q to 0, you get better asymptotic guarantee, but the finite N performance will suffer because this guarantee is valid only for N greater than some function of Q. All right. Also, we proved a lower bound saying that no algorithm in this distribution oblivious setting can get exponential decay for probability of error. So in some sense, no algorithm can do better. You can do better in constant. That's all, right? This can get very close to exponential decay. No algorithm can get close to exponential decay. Okay, so that's best term identification with CVAR and heavy tail. And nothing is known about the distribution. There is also some fixed confidence best term identification. Fixed confidence I didn't speak about at all. There are some important papers there as well. I don't think we have the time to go over any of them. There's a whole bunch of references that I think there's a lot of references that Prashanth has put out here. I don't know if you want these slides, we'll give them to you. And you can put them on the page, right? What else do we have to remark? Oh, that's.
Oh, this is the answer to my question.
So we are not going to make any money. Yeah. So knowledge. Yeah. Thank you. Thank you very much. Which one?
The last previous section. Minimize the regret and the risk.
Yeah. So the objective of so this is this one, right?
So like this one also would be like y minus some rated y minus CR5 and use it for like maximizing my reward and minimizing risk.
Yeah, all that is possible in the CR. So in this tutorial, we made a little bit of a mess of whether you're looking at rewards or losses. Okay, so whether you want to minimize or maximize CVARs and means is.
But then like going from regret to risk, because everything is minimization, so it's all minimization. Going from maximize to going from reward to risk, min-max problem, right? Because you're maximizing.
Correct, but this is best term. So best term means least risk. So I want to minimize that quantity. This is best term under fixed budget. Okay.
Do you have an algorithm like LCDs? LCDs maybe PK now which has maximum reward, like but has a least.
That's what you want, right? So yeah, you can do all that. So mean variance, for example, is an algorithm like that. So I mentioned Vincent Tan's paper in 2020. It's mean plus variance, not CVAR, but you can do linear combinations of any two risk measures, mean plus any constant times risk measure you can work with.
But in LCDs, you want always
Yeah, I mean LCV or UCV depends on whether it's maximum. That's okay. Small matter. Anything else? Yes.
So this is about sampling from the syntax.
Huh.
That, are you sampling from the water
No, it's a simplex. It's a uniform distribution over the simplex. See, if it's with probability 1, you will be in the interior, right? No. It will be a probability distribution of that dimension. So if you have 21 samples from a arm, you will look at a 21 dimensional simplex, which is a complicated piece, and you pick a. So what will a typical point from the 21 dimensional simplex be like? It will be a bunch of positive numbers that add to 1. Correct? See, if you are in the if you're in the triangle, you will be in the interior. No, that is.
So you won't be at one of the 3 coordinates, but you can be along the.
No, the 3-dimensional simplex is the set of all P1s, P2s, P3s, which are greater than or equal to 0, such that sum over Pi is equal to 1. That's the simplex. Probability simplex. It's as simple as that, right? So nk dimensional probability simplex, you take a uniform sample, then you calculate mean or CVAR with that distribution. And then you play the arm with the best mean or CVAR, and then you get a reward. Update your reward vector, update your nk vector. Finished. Okay. Algorithm is easy to understand, but the analysis is quite intriguing, and optimality is quite intriguing also. Okay, but I think the chapter is finished. It settles optimality of Thompson sample for good. Of course, you can extend, and you can try extending it to sub-Gaussian classes or anything. I don't know if that's possible. But the key step is that Ryu Honda have gone from very specific parameter classes, such as Gaussian, Bernoulli, multinomial, all that, to any bounded unparameterized distribution class, right? I think that's a big leap. Thank you.
Yeah. Any questions? Okay. Please continue. Have some more questions.
Thank you for attending.
We moved on most of the questions.